device actually influence the property of a material? Is that okay? So in electronics, we are talking about how we can manipulate these electrons and other charges. And apart from electrons, there are other charges. Is that okay? We have the protons. So we can also talk about that. We have the neutrons. We can also talk about that. So they are very important. Now, under electronics, we have a very two broad perspective. We can talk about analog electronics. We can talk about digital electronics. When I was teaching this one to the undergrad, they were not able to really relate with the analog. But I think we may be able to relate it because there are some things here that we are very familiar with, like the analog radio station. Now you don't even need that. Like even now, the young phones that it has come, you press, then you wait for some seconds, then you get a different channel. It's not like the olden time that you have to move a knob, either clockwise or anti-clockwise. Then maybe be tuning the antenna till you get a signal, you know. So these are how analog and digital has been diverse. Is that okay? Now in the analog, we are actually trying to vary some voltages and some current. And at the end of the day, we get a signal. But with the digital, it's not like that, actually. We are just talking about discrete values of interest. And a very typical one is, say, let's say zeros and ones. We know that if it's this, is this, if it's this, is this. So it's either we increase it to the extreme or we lower it to the extreme. And in fact, all the devices that we've been getting for the past decade, they are all based on digital electronics. Is that okay? The transition is phenomenal. Let's hold on to this. I'll come back to it. My question today is there any difference between electrical devices and electronic devices? But before that, let's give an example of electronic devices. What are some of the examples of electronic devices? Any idea? Yes, say well.
An electronic device can be a
transistor, okay. Any different submission? Yes, Ramon.
So we may have diodes and then resistors as well.
They may have diodes and resistor, but it's a phone electronic device.
Yes, please.
Yes.
Say lucky.
Yeah, say laptop. Laptop is also one.
Okay. So now
Maybe
let's go.
computer, those kind of things, calculator. And
Okay, they're all electronic devices. Now let's look at electrical devices. What are some of the examples of electrical devices?
Washing machine.
Washing machine, okay.
Electric fan.
Electric fan, okay.
The bulbs.
The bulbs. So a quick question. Why is a light bulb an electrical device? Why is a washing machine an electrical device?
Okay, sir. So on the light bulb, it's an electrical device because it will convert electricity to another form of energy, which is light.
Perfect. So with electrical devices, we expect that there's a form of energy changes or transfer or conversions. So for the electrical device, we change, let's say, electrical energy to any other forms that is of interest, like the light, like the washing machine, the motor is moving, like heat from the iron and other things. But with the electronic device, it's not like that. Is that okay? Because that one typically depends on electrons and their movement. Is that okay? So these are very important between electrical devices and electronic devices. So anytime you are talking about electronic device, it's a whole thing on its own. We can't make the two of them for it to work. Is that okay? In as much as they work hand in hand, they are all two different things together. Is that okay? You can't tell your phone to convert one form of energy to another form of energy for you. The energy that is given could be part of the dissipation process, but it will not convert it fully for you. Now let's look at something. We are going to our basic things that we've learned before. Now let's look at matter, elements, and compounds. Now, as and now, we all know matter, so I'll not go through this. Now, these are also very important. I want us to identify the terminologies here. Anytime you are talking about a substance that cannot be chemically decomposed into smaller substances, like gold, silver, oxygen, what comes into mind? Which terminology comes into mind? Maybe let me give you a hint. I have compound, molecules, atom, elements. What terminology comes into mind? Any idea?
So is it element?
An element.
It's element.
I don't know.
Element.
Okay, it's an element.
It's element, yes.
Oh, okay. So let's go to the second terminology. A substance made of two or more elements combined chemically becomes what terminology?
Compound.
That's a
Molecule.
compound.
So the smallest particle of a compound that retains the compound chemical properties. And a typical example is oxygen gas. That's O2. What is this?
Atom.
Is that
No, it will be a molecule. Oxygen
Mm.
gas. Oxygen gas is a molecule.
Let's think about these terminologies very well. They are important. Now let's go back to our basic atomic theory too. As of now, 2026, we know that anytime we are talking about an atom, we are talking about something that has something we call the electrons, something we call the nucleus, which in the nucleus composed of the protons and the neutrons. And we know that the electrons has something they are orbiting in. In fact, during Rutherford, he told us that the atom actually behaves like the planetary system, where we have the sun sitting at the center and the planets moving around. And they all have a particular path they have to move. In fact, during that time, there were a lot of confusion and manipulation about all these things because Rutherford was saying something different. Bohr was saying something different. Chadwick was saying something different. Is that okay? But as of 2026, we've all concluded on the model of how the atom is supposed to look like, where we have the nucleus, electrons, which for every atom with a particular element, we can find the atomic number and atomic weight. Now, when we are arranging the electrons on a shell, let's say we have our first shell, and we start counting the shell from the one that is closer to the what? To the nucleus. We start counting from here, we go, then we move outside. Now, a quick question. The first shell and the last shell, which has more energy?
The last year.
The last shell, perfect. Is that okay? Because anytime, from what Bohr said, anytime a shell is at the top there and it wants to come down here, it has to give off some energy. Meaning the energy that it needs to stay here is supposed to be less. In the same way, if this electrons at the last shell wants to move up, it has to get some form of energy to move up. Is that okay? So, and the energy can be in so many forms. The energy can be in the form of light, can be in the form of heat, is that okay, or any electric field. And it is a typical phenomena in a practical way. That is why, the rosary that Catholics use when you like incident light on it for some time and you put it in darkness, it glows. It's okay, a very typical one. So when you give it light, all the electrons here get excited and go up. But when there's no light like energy, it get de-excited and come down again to the original state. In the process of coming down, and it gives off some form of energy. And that form of energy is what we see it as a light, the glow. Very nice. Even some wrist bands that we put on our hands, it glows. Is that okay? And we call it phosphorescence. It takes time before what it glows. There's another phenomenon that we call the fluorescence. But that one, the time that it takes to de-excite is very short. In a nanoseconds, our eyes cannot see. But the phosphorescence, it needs a lot of time before it can dissipate the form of energy. Like we are talking about seconds to minutes. So our eyes see the glow. And with time, you see that all the light is fading off, kind of. It means the energy is given out, it has given everything out. Now, anytime we are arranging electrons on each shell, there is a particular formula that we can use. These are all recaps. I know you know this. So we have a formula like this, where n here is our principal quantum number. Principal quantum number is dependent on the number of shells. So the one that is close to the nucleus has a principal quantum number 1, 2, 3, and it goes up. This formula is just telling me the number of electrons that I need on a particular principal quantum number. So let's say I'm working on the first quantum number, the one closest to the nucleus. It means my n is 1. When I square the 1, I'll get 1. Multiply by the 2, then I get 2. So it means I need 2 electrons to fill the what? The first shell. Then it goes on like that. Now, anytime we are doing this kind of an arrangement, the last shell that we have here, we call it what? The valence shell. Exactly. And this valence shell is very, very important. In fact, it's really crucial in form of some of the physical properties and the chemical bonding of a particular element. And even the valence shell will let you know where the element will be placed at in a particular periodic table. Is that okay? So when you look at the element and the valence shell, you know that okay, it is at group 1 or group 2 and all. Is that okay? It is very important. Now we are going to base on this valence shell in all our subsequent studies, because that is what electronics is interested in. Please, are we following?
Yes, please.
Perfect. Now, let's look at this. This diagram is quite complicated, but let's forget everything, then concentrate on what I've zoomed in here. Perfect. Now I have this element, the nucleus is here, the electrons are here. So I have the first principal quantum number, the second principal quantum number, the third quantum number. We know that the last shell that is here is called the valence shell. In fact, after the valence shell, there's another shell that is up there, but there's nothing on it. Electrons are not on it. But there's another shell here, and that shell, we call it the conduction band. And this conduction band plays a very critical role here, because the behavior of the number of shells that we have at the number of electrons we have at the valence shell actually influences the property of the element. So let's say we have an electrons at the valence shell, and the electrons is about 1, 2, or 3, very less. It has a flexibility to move from the valence to the conduction. But let's say if we have the electrons at the valence to be very small, it's very hard for it to move, because when it's small, the nucleus tends to hold it together to the what? Together with the atom is like a structure. So let's say we have electrons at the valence to be, let's say, 5, 6, 7, 8. It is very difficult for the element to have its valence electrons move from the valence shell to the conduction. And you know, as I explained earlier, the electron movement actually influences the property of what? Of the material. So it means that if we have an electrons that cannot easily move, it means the material becomes what? Is it a conductor, a semiconductor, or an insulator? Can someone help me?
The question again.
Okay.
So I am saying that if we have a material and the electrons are not able to move freely, would the material becomes a conductor, a semiconductor, or an insulator?
An insulator, say.
An insulator.
Honestly.
Perfect. Now, if we have a material and the electrons are able to just jump from its valence to the conduction, then the material becomes a typical what?
Conductor.
Perfect. So this explanation that I'm giving is very important. And I'm saying it again. Anytime we have an atom and the valence electrons that is there is less, it means the electrons can move from the valence to the conduction. The conduction is just empty space. But because the electrons are less at the valence, it's able to move. But if there are more, the nucleus hold is tight to each other and it's very difficult for it to move. Is that okay? So typically, it means that anytime we have an element and we see the electrons at the valence, we can know whether the element is going to be a conductor or an insulator. Please, are we getting it?
Yes, please.
Perfect. Now, let me show you something. Let's look at only this part. That I'm going to zoom in only this part. Now, this part is the valence. This part is the conduction. And as I said earlier, if it's less, it will move to the conduction and come back. Conduction and come back. Conduction and come back. Easy movement. But if it is more, it just stays there. It doesn't move at all. Now, in between the conduction and the valence, there's another band there, and we call it forbidden band. And there's even a particular energy level there that we call the Fermi energy level, which I will show you later. Now, for a single atom, we expect it to behave like this. So we have the valence and we have the conduction. And as I said earlier with the ball, if this one is close to the nucleus, it means it has less energy. If it's far away from the nucleus, it means it has more energy. So their energy levels as it's going increases. Is that okay? But because of its flexibility, it can move here, come back, move here, come back, move here, come back. If we have a lot of atoms, it means we have a lot of movements going on in there. And of course, if we have a crystal lattice, we are going to have a bulk of them like that. Now, let's imagine this. You have a matter, a solid. And in the solid, you know, for a particular solid, that is about 1 gram, we expect about 10 raised to the power 9 of protons inside, which is equivalent to the number of electrons that is in. So it means we have quite a number of them when we have, let's say, a stone that is weighing about 5 kg, a lot of atoms and protons. Now, if we have one atom that we are using as a demonstration here, and we have the shells, and we have the gap, and a single atom like this, another single atom like this. If the atoms interact with each other, we should be expecting a band like this. Because at the end of the day, the conduction bands, the electrons at the conduction band and the valence band are able to move among each other. Is that okay? So it's not like the conduction band for each atom has its own and the valence has its own. They all will have a common conduction band and a valence band to move moving between. And if we are to classify them into material level, from the explanation that I've given you earlier, it means that if we have easy movement, we may have the conduction band and the valence band in here to be very close. In fact, they are even overlapping because of the easy movement of electrons at the valence to the conduction, from the conduction to the valence, at the valence to the conduction. When you take a material like an insulator, it's very difficult for the electrons to move. They are stacked at the valence. And because of that, their forbidden band or gap tends to what? Increase. So it's hard for an electron here to jump from this end and go straight to the conduction. It will just stay there. I don't know the energy you give it to it for it to be able to cross this gap. So it will just stay there. And even if we are giving it a particular energy, it means we are going to exceed our absolute zero. It's still not going to reach there. It will be very difficult. Now, in between the insulator and the conductor, we have a material we call the semiconductor. And one insulator and also a conductor. So it doesn't have a very wide forbidden band like the insulator, and it doesn't have an overlapping band like the conductor, but they are very close. Now, there's another thing that I want you to keep in mind, that is the Fermi energy level. And here is just talking about the highest energy that electrons can reach at absolute zero. When you're talking about absolute zero, you're talking about 0 Kelvin. So at 0 Kelvin, this is where it's able to reach. At 0 Kelvin for semiconductor, this is where it's able to reach. At even 0 Kelvin, the material can still behave as what? As an insulator. Sorry, as a conductor for a conductor material. Is that okay? So the Fermi energy is very important. Any questions so far?
In short, it means that the Fermi energy level is just talking about the gap between them, which is the forbidden band.
So the forbidden band is this whole thing, from this end here to this end here. And when I was explaining this thing, I told you that if an electron even wants to move from the valence to the conduction, sometimes it needs some form of energy like heat, light, and other things. Is that okay? So let's say we don't give it heat. At a normal temperature, or let's say at a zero temperature, which energy or which level can the electron reach? Is that okay? When you look at it as a conductor, at 0 Kelvin, still the valence here can move to the conductor because it's overlapping. Look at where the Fermi energy level is. At 0 Kelvin, the Fermi energy is here. So it means that if we exceed the 0 Kelvin, it could be that for a semiconductor, it may reach a conduction band. So this is 0 Kelvin. Let's say we go up to about 25 or 30 Kelvin. It means it has more energy. It may reach there. But for an insulator, at 0 Kelvin is this. It's still very wide for an electron to reach the conduction, even if we exceed or give it more temperature. I don't know if I am making sense a bit. Is that okay? 0 Kelvin is literally not giving it energy at all. If we are at room temperature is about 25 degrees Celsius. It means maybe we have some form of heat there that can be given to the electron as a form of energy. Is that okay? And it's very common for a conductor to move, or even a semiconductor to behave as a conductor when it is at room temperature. Because when it's at room temperature, at least we will exceed the Fermi energy level, because at room temperature it has exceeded the 0 Kelvin. So at least we may move to the what? The conduction band. But when you look at the insulator, it's not like that. Is that okay? Even the Fermi energy level is at the center. We give it more energy even at the room temperature. It's still not going to reach where we want. That is going to be difficult for it. So are we getting it a bit?
Yes, sir.
Yes, Azuma.
Okay, sir. Please, I want to find out from you. During your explanation, it's like you made mention of that are the valence electrons or the valence cell. If it is having a small electrons, I don't think conduction will occur. And if it is having a more electrons on it, that's where the conductions will occur. I don't know whether if I'm right.
So I said that if we have less electrons at the valence,
okay,
the electrons are able to move easily to the conduction. Less electrons at the valence is able to move at the conduction.
okay.
And the movement of an electron influences its conductivity.
Okay.
Because if the electron moves, that is where we get the material to be conducting. Now, if the electrons at the valence are more, they're not able to move at all. Is that okay? And
Okay, okay.
that is how we have an insulator.
Okay, thank you, sir. And my question now is, at what number of electrons can we consider as less or more?
That's a nice question. I think I stated it, but let me just repeat. So we are talking about 1, 2, 3 to be less, and 5 going to be more, and electrons, that is about 4, mostly represent a semiconductor.
Okay, thank you, sir.
You're welcome. Please, are we okay? Okay, so now let's move to another. Now, I'll move into a next slide. Then I want you to try this for me. I beg of you, don't use AI or anything. Just solve it. I'll give you just 5 minutes to do that. It's about 5 questions, objective. So read and solve it. I'll come back, then we all go through together. Just to know your understanding of what we are doing. I beg of you, yeah. So just go through, take your time and just go through. So this is the number one slide and another slide. So I don't know if you can take a screenshot.
Okay, sir.
Have you taken a screenshot?
Yes.
Yes, please.
Then this is the second slide. I'm making you take a screenshot because I'm stepping out briefly. So within, I'm giving you 10 minutes for it. I'll come back right now, then we'll go through together. Have you taken a screenshot of this one?
Yes, sir.
Perfect.
Please bring the
Sir,
one.
please, I missed the first one.
The first one, this is the first one.
The first one.
This is the first one. Number 1 is here.
Mr. Samson Kujo, how are you?
Mr. Schizo. Charlie, thanks, Ade.
Hello. Please, are we done?
Yeah, we are done.
Oh, perfect. So, number one, element with one, two, three valence electrons usually make excellent. What's the answer for this?
It's
Conductors.
conductors. It's conductors.
Perfect. What is the primary reasons for the electrical conductivity of metals? So we have large energy band gap between the valence and the conduction band. We have an overlapping valence and conduction band. Electrons are tightly bound to the atom, and lack of free electrons in the conduction band. Which one is the answer?
B.
It's
B.
overlap with the balance.
Okay, perfect. Now, what is the energy gap between the valence and the conduction band in insulators? How wide is it?
Why?
Wide, very wide.
Very wide.
Very wide. But I don't see very wide here.
Wide.
Wide.
You've added more adjectives to it. Okay. Now let's go to the 3 and 4. What happens in a semiconductor when energy is supplied? Like we're talking about energy like heat or light. Electrons, the first one is electrons move from the conduction band to the valence band. Electron move from the valence band to the conduction band. Electrons could combined with holes, the forbidden band with rate increases.
They
Say
move
B.
from the valence to the conduction band.
So electrons move from valence band to the conduction band. Perfect. That's a win in the F. Yeah, man. And you prefer ahead, yeah.
Per your explanation, it make it easier for understand.
Hold on a minute, please. Okay, sorry. I'm in the lab and during weekends we take level 100s, level 200s, and some of the level 300s through practicals. And there's a lot of pressure here, so I'm alternating between them. I go a bit. That's why I left to go and check on them. They are the people there are only the technicians, so I needed to go and check them out and make some calls so that we get some people to come and help too. So sorry about that. Another pressure this semester. So let's go through the last one. In a semiconductor, what is created when an electron from the valence band moves to the conduction band? What was the answer for this, please?
A hole.
A hole is
The
created.
hole.
But are we all following? Did we get some marks there? How many people got 5/5 without using online?
Say I had 5, but I wasn't sure of the number 5, so I just chose L.
Okay, so let's say 4.5.
Yes.
I had 4 over 5.
4/5. Which one did you get it wrong? The last one.
I think the number 5 years.
Okay. But who was struggling here? Because this is the earliest part and it's very cheap. The subsequent ones is a little bit dicey, but you will be okay. It depends on. I'll try as much as possible to explain it well. So please explain small. Which part should I explain small?
Stragglers are around.
Okay, so let's go through together. Number 1 and number 5. Can someone help us explain the number 1 and number 5 for Yebua? So maybe let's start with the number 1. Stay lucky.
Right.
Yeah, can you help me explain?
The number 1, you said that when what do you call it? Electron in the valence shell influence the property of the element. And so for that matter, when there's more valence electron, that means the insulator is happening is likely to occur. When the valences are more, when they are more, insulator occur. And when they are less, that means conductor or conduction may occur. And so per question 1, is it element with 1, 2, or 3 valence electron usually make excellent one. And so we have you said that when we have 1 up to 3, that means that's what do you call it? That's less. So from above 5, I'm going, that's more. So for the question, we have 1 up to 3, so that means that's less. So when it's less, conduction okay. That's what the question one answer is called B, conduction.
Good morning, all.
Okay, good morning. Sir Lucky, thank you. Any other submission? Say, boy, are you okay?
So I want to
Yes,
add
please.
a little to the question one. Closer.
Yes, please. I'm listening.
Yes.
Can you-
The question one said when it is less, it means that there is movement. They are able to move. And then free movement causes it to be a conductor. And so that is how come the answer is a conductor.
Okay, very perfect.
So, and
Yeah.
it's adding up when you take an element like sodium, atomic number 11, it has a valency of 1. When you take aluminium, which is also a metal or a conductor, it has atomic number 13. So the valence shell, the 3 is within, so the 1 and the 2 and the 3, they are all within the metals, and metals are conductors. That's why I chose the D.
So you came from the chemistry part. Okay, that's perfect. Yes, Raymond.
Okay, so for 1, 2, 3 electrons, they are less bound to the nucleus, and so they are free to move to the conducting band and then back to the valence band.
Perfect. So now let's go to the number 5 and explain it to Sayeboa. Please, who will help me? But let me ask Sayeboa a question. What did you choose here? What was your answer for the number 5? So that we know your understanding. Hello, Sayeboa. Okay, 4. Iron. Okay. So those who had the number 5 correct, help us here. Why is it a hole and not an iron?
I didn't get it correct, but the explanation I had is that when an electron leaves a valence band, it leaves behind an empty space, and so that empty space become a hole.
Okay.
I don't know if
Any different submission? Sayeboa, are you okay?
Yes, sir. Yes, sir, I'm okay. Thanks.
You're welcome. Now, so in classifying these solids, they are literally very important. Talking about insulators and how their conduction band behave, how their valence band behave, how their energy band gap also behave. They are very, very important. In fact, they are even how wide, as this is wide, in insulators, we have some that varies in wideness. So we have one that is very wide, they are all wide too, but in their wideness too, we have some variations. And it influences the property of the material a lot, which we will be seeing that in our subsequent slides. Now, if we have a particular insulator, we expect that at ordinary temperature, is that okay? All the electrons are filled in a valence band. And in fact, the conduction band is completely empty, and we have a very huge or large energy band gap. Now, in conductors, interestingly, is the opposite. They are literally overlapping, and they can just move up and down, even at 0 Kelvin. Is that okay? So even if you don't give it any source of energy, the electrons has the flexibility to move up and down. Now, in semiconductors, it's quite different. Semiconductors behaves like a conductor and as an insulator at the same time. And that is why it's very important for us. Because if I have a material and I can control its conductivity, it means the material is perfect. Is that okay? I can control its conductivity in the situation where I can manipulate the data the material, so that I can know that, okay, this is the level of conductivity that I want for a particular application. And that is what we've been using for the past more than decades. Is that okay? Very, very important. And when we reach the part 2, I'll show you how big a semiconductor was before. Very, very big. And how small we can get a semiconductor now. In fact, every year, either iPhone or Android or any Samsung product, they update their memory chip in their phone. They will tell you that now we've upgraded the phone. And it's true, they've upgraded it. If someone is using iPhone 17 and someone is using X, the control is different. This one is literally fast. Everything is fast, more features and other things. They've added a lot of things to it. And when you look at the things that small chip is doing, the olden times, before you get a chip to do that, you have to build a chip like a house before it can control that work. In fact, even the olden times, if we have a memory card that has a space of 32 gigs, you need it as a room, as big as a room. Now we can have a hard disk, either SSD or HDD. That is about 5 terabytes. I have one 5 terabytes sitting here. Very, very small. 5 terabytes is a huge data capacity. Is that okay? That is the growth of how semiconductor has led us to. So if I can control some properties of a material, then it means the material is good enough for application. Is that okay? Now let's come back to the basics that we are looking at. Now, if I have a semiconductor, in fact, at low temperature, let's talk about, say, 0 Kelvin, I don't have any electrons at the conduction. They are all filled at the valence end there. So at 0 degrees Kelvin, at 0 degrees, or let's say at 0 Kelvin, we have the material behaving as a typical insulator. Is that okay? Because electrons are not moving. Now, let's go to room temperature. At room temperature, fairly, we've moved from the 0 Kelvin. So at room temperature now, at least there's a form of energy that the electron can use to move from the valence to the electron. But we have to know that it's not a huge energy. So we are not saying the conductivity has reached a level of a conductor, but at least there's a movement of electrons there. Now, as we increase the temperature, we can also increase the conductivity of the material. Is that okay? Because as we increase the temperature, the electrons here get energized enough to move from the valence to the conduction, because it has gotten energy. Is that okay? So we move, then goes, it moves, then goes. So hence, the conductivity of the semiconductor increases with what? With temperature. Temperature is a form of energy. Even if you don't give it temperature, then we give it something like light. It's also a form of energy. It's possible, it's going to work. So here I've classified the resistivity of these 3 materials that we've gone through so far. Now when you look at insulators, anytime we have insulator that has its resistivity to be more than 10 raised to the power 5, then the material is an insulator, right? And anytime you have a resistivity that has 10 raised to the power negative 3 to 10 raised to the power 5, the material is a typical semiconductor. Anytime you have a material that has a resistivity to be less than 10 raised to the power 3, negative 3, it's a conductor. Now, there's one thing I want you to know. Even in conductors, it has a form of resistivity. Is that okay? It has a form that opposes its flow of electrons or current, because you know that current is very dependent on electrons flow within a particular area. Is that okay? So it opposes it one way or the other. And there's a lot of things also going on, collusion and other things. And these collusions causes the heat and other things. So at the end of the day, even if you are a conductor, it has a form of resistivity. Is that okay? And if you remember the formula for resistivity, it's very dependent on the resistance, very dependent on the length of the material, and very dependent on the area of the material. Exactly. So all these things plays hand in hand. Now, the question for the class, if I have a material and it has no resistivity at all, which material will it be?
A superconductor.
A superconductor, perfect. Thank you very much. It's because of a superconductor. Zero resistivity. Now let's go to what is of interest. That is the semiconductor. And that is where we are going to channel our energy at. So we forget about conductors for now. We forget about insulators for now. Typical semiconductor. Now, semiconductor materials, a typical example is the silicon, the germanium, the gallium arsenide, and other things. And you know, these materials has a very few free electrons, as I explained earlier. Their movement is very dependent on the energy you are giving to it. Apart from giving it energy to move, there's one form that we can increase the electrons in the material, and that is what we call adding impurities to the crystal lattice. So a typical crystal lattice is something like this. They are all typical semiconductor, very typical semiconductor. So if it's silicon, they are all silicon, no impurity. So something like this, we call it intrinsic semiconductor. Now, we want ways where we can free the electrons. And as I showed you earlier, one way is giving it a form of energy, like heat or light. Another way is adding impurities to it. Is that okay? So when you add the impurities to it, you get a form of access, either holes or electrons. And that will also increase the resistivity of the what? Sorry, the conductivity of the what? Of the material. It's like in a class, they are all boys. But in a class, because they are all boys, they are not energized. And now the school decides, let's bring a mess of LED in to energize the boys. Now we drop a LED in. Is that okay? And they get energized. But before that, there were other ways of energizing them. It could be that we are giving them some allowance. It may be that we are giving them some sport ways. Is that okay? But another way that we can also increase the conductivity is adding impurities. And it has a process. And the process is called doping. Is that okay? So the impurities can be either a donor or acceptor. When you are talking about the donor means is giving. And if it's giving, it means giving like electrons. Is that okay? When I keep talking about acceptor, it's accepting something. So the acceptance is going to be like a hole that is sitting there, that it has the ability to accept an electron. And then the doping, we don't need much. Like the boys in the class, they don't need five ladies in their midst before they'll be okay. They need only one. Let's say a full SHS, there are no lady there. They say, let's drop only one, and it will get the boys energized. Is that okay? So even if we have about 10 millions of these atoms, we need only one impurity to make it okay. Is that okay? And interestingly, it works. So depending on the property that you want or the level you want the semiconductor to reach, depending on the application, that will influence your doping process. But at the end, even if you have one impurity in 1 millionth of an atom for a semiconductor, it is fine to become a what? A conductor. Now you can imagine this one like a crystal lattice. Is that okay? A very typical intrinsic semiconductor. This is a 3D form. If you get a chance to do a material science, there's a lot of interesting things you can do under crystalline lattice. And I think my time they were teaching us around level 300. Very interesting topic. Now, if we have something like this, you can imagine this one at the top, only the top view. Imagine it as what we have at the down here. Phosphorus is an impurity. If there's no phosphorus, I'll show you how the structure looks like. And when there's phosphorus, I'll show you how the structure looks like. So let's hold on to that. Now let's do a little history, then we'll go back to the doping process. In fact, at first, one semiconductor that was mostly used was the germanium, sorry. Gemini is AI's platform, so germanium. So the germanium was a very common semiconductor that was used. But with time, it has been replaced with one that we call the silicon. And there are two important things what the silicon can do that can surpass the germanium. In fact, the silicon is very abundant, very, very abundant. Is that okay? And I don't know, do you know any idea where we can get silicon? Any idea?
So we can find it in solar panels.
Okay, no, I'm talking about the natural sources that we can mine it.
Okay.
So the solar panel is the end product. Because solar panel too is a form of a semiconductor. Is that okay? But where do we get it before we can, in a raw state, before we can get the silicon from? Any idea?
No, sir.
Okay, so a very common
We
way.
have no idea.
Come again.
I say no idea for now.
No idea. That is fine. A common place that we can get it is the seashore in sand. So we mine it in earth like we mine gold, but we don't have to dig deeper and explore the land. So the seashore and everything, they are all full of silicon. Is that okay? It is so yeah, a lot of silicon, very, very abundant. Is that okay? So mining a silicon is not a big problem. Now, apart from it being abundant, one important thing that the silicon has that the germanium don't is the energy band gap. In fact, the silicon has a wider energy band gap than the germanium. And now you know the energy band gap. I'm talking about the forbidden band. That space between the conduction band and the valence band. And if it's wide, it's good. Because anytime it's not wide, small form of heat will let electrons transport, making it very not stable. But if it's wide enough, not as wide as an insulator, but if it's wide enough, I know how to control the temperature, the conductivity, and other things. Is that okay? So it is very, very important. So the energy band gap, that is where we have the Fermi energy in between. That is why we have the forbidden band there, the upper part. So the silicon is very important as compared to the germanium. Is that okay? But if you are asked a question like this, I prefer you use the energy band gap to explain why we need silicon more than we need germanium. If you want to add up, you can add how abundant they are. But don't go and write the abundance first before you write the energy band gap. Is that okay? And even if you write only the abundant, the marker can decide not to mark you correct. Is that okay? It's just an add up that I did. But the main reason why we have silicon than the germanium is their energy band gap. Now, we have a lot of applications of this. Our solar panels we use, say mentioned, our phones that we are using, our LEDs, our television. Now, even our television, a typical semiconductor component, every part, from the LCD to the back components and electronic components. Now, it's very cheap. At first, television wasn't like that. Only the rich were owning television in quotes. But now it's very because we can easily make these materials. Is that okay? It wasn't like the olden times where they used the cathode ray tube process to make a television, where they have to get a lot of the powder, this fluorescence powder inside, a lot of process, But now this semiconductor has made materials very cheap and making them more accessible to everyone. Is that okay? So apart from getting the elemental form of a semiconductor, we also have compound semiconductor. When I say compound semiconductor, we are combining two elements to form a semiconductor. Now, in a typical elemental semiconductor, we have this group representing them. We can talk about the carbon, we can talk about the silicon, we can talk about the germanium. Which compound is this? So which element is this?
Tin.
Tin.
Tin, very good. We can talk about tin. So they are all parts of the what? Semiconductor. Which element is this?
Lead.
Lead. Okay. Now, apart from the elemental semiconductor, we can have compound semiconductor. Compound semiconductor is just merging two elements to form a semiconductor. And interestingly, anytime you combine group 3 and group 5, we get a semiconductor. In the same way, anytime you combine group 2 and group 4, we get a semiconductor. We can go through this, but that is not of our interest right now. So we will hold on to the bonding process between them that causes the semiconductor. So we hold on to that. Now we have one that we call the ternary materials or semiconductors. This time around, we are combining 3 different elements to form what? A semiconductor. Like the mercury, cadmium, telluride, like the gallium aluminum arsenide, like the gallium indium arsenide, like the gallium indium phosphide. Is that okay? We combine 3 of them to form what? A semiconductor. So for semiconductor, even we have the one that it has been made lab prepared, like the ones that we are combining some different form of elements. Is that okay? We mine some of the elements, and some of the elements after mining, we combine them in the lab to form a different form of a semiconductors. And it helps because you get the flexibility to control it how you want the material to behave. Now let me show you something. These are some of the semiconductors and their energy band-gap. These are the elemental ones, and these are the compound ones. Now let's look at something. The silicon and the germanium. You see the silicon has 1.12. Look at the germanium, 0.66. So adding up to the explanation I made earlier, where I told you that for a particular germanium, we have a smaller wide band gap, and the silicon has a wider one. Is that okay? That is why we need the silicon. So you can see how huge the silicon can be and how low the germanium it can be. And this is good in our manufacturing. In fact, at Kanipapemua, we can actually use the carbon on, but it is expensive. Imagine your phone made of diamond, because you can't use the raw state as carbon to do the manufacturing. Is that okay? Because look at the energy band-gap. Very huge, like 5.4, 5.5. Is that okay? But we can't have a phone made of this kind of material. It will be so expensive for us to purchase. Is that okay? So the energy band-gap actually influences the material usage a lot. Any question before I move on to this? Can I go on?
Yes, please.
Okay. I'm just hoping you are understanding things. Yes, Ebuam.
Sir, I wanted to ask. In your submission, you made a statement about the conduction of a semiconductor. You mentioned temperature and impurities. Please, are they the only two?
So they are not the only two. Temperature, the two that we can classify them is the doping process and the energy process. Is that okay? And on the subsequent slides, so I'll show you something we call the diffusion process. And the diffusion process is talking about the fact that is how solar panel actually works. One way of getting electrons move is when they are concentrated at one end. They don't like it. They'll just move and fill every end. Is that okay? So that is one way of moving electrons. And the whole process is we want to move electrons. So it's not particularly temperature, it is particularly giving it energy. And temperature is a form of energy. If you give it EM field, it is a form of energy. If you give it light, it's a form of energy. That is why I use the rosary as an example. Is that okay? That it glows. The wristband, some of them, it glows. It's a form of energy. So we are interested in the form of energy given to it. And one way of controlling it is the doping process too. So it's not only two. Is that okay? In this slide, we are talking about the energy, which contains the temperature and the light and other things. We are talking about the doping, and we talk about the diffusion process. Please, are you okay? Now let's go on to silicon, a very typical semiconductor. Now silicon has valence electrons of 4. So we have 2 at the first quantum number, 8 at the second quantum number, and we have the last one as 4. In fact, how silicon behaves, because of the 4 that it has at the outermost shell, it can create a good structure as a lattice. So it has to bond to get a very good structure. And in the process of bonding, it uses one particular process called the covalent bonding, which we are all familiar with one way or the other. Now, how this is working is because, let me use a pen to write. Because the silicon has 1, 2, 3, 4, only 4 valence electrons. Is that okay? There's another certain silicon beside it that will share its 4 too. So this one, the silicon down here shares the other one at the top. It also share the one with the left, share the one with the right, share the one with beneath. Is that okay? And another one goes down, like millions of them. So they share so that they get a very strong bond to form the crystal lattice. So please keep it in mind that at the end of the day, this bonding is called a covalence bond. And the reason why we need this one is to form our strong crystal lattice. Now, if we do something like this, it is very, very, very difficult for an electron to move. In fact, it could be that electrons will not even move at all. And even if it moves, we will get a very few of them moving. Because how it will move is maybe this one will eject, goes here, create a hole. And the hole that it creates here, this one will come and fill it. Is that okay? So their movement is not that extreme. And as I mentioned earlier, in a situation like this, that is where we have our intrinsic. Is that okay? And it has no impurities. So we can control the impurities procedures. Is that okay? We can control the impurities by adding the holes or the electrons of interest. Now, before I show you the impurities, there's something that I want to show you in terms of electron movement. And we call that one drift velocity. I don't know, I think I taught you this. When we have two charges, charge 1, let's say negative, and charge 2, let's say positive. And I have the distance between the two charges as R. And I'm interested in finding the force. But anyways, in a situation like this, are we talking about force of attraction or force of repulsion?
Attraction.
Force of attraction. So now if I want to find the force of attraction, what would be my formula here?
It will be Q over the charge over the 4 pi permittivity R square or something.
Come again.
It will be F, that's the force equal to Q, that's the charge, over 4 pi permittivity R square, that's the distance square, if I'm right.
Okay, you are almost there. Come in, someone should come in and help us.
The product of the two charges multiplied by K divided by R square.
Okay, perfect. So you have a situation like the K, that is a constant, right? Which constant is this?
Coulomb's constant.
Perfect. So we have this. Then we have our R square.
The permittivity.
So our K1 and our Q2 is okay. Now after this one too, we did something. We did something that we said electric field, where I even explained the fact that if you have a house, you have your territory. It's like placing a magnet on the floor or on the table. It doesn't mean that magnet will attract every metal on earth. It has its field that it operates. If you come to the field, that is where it attracts you. The same way charges to behave. If you are not in its field, it has nothing to do with you, right? So in a situation like that, we have a formula that we can calculate the electric field, combining the force and the charge itself. Do you remember the formula?
E is equals to force on charge.
E equals what? Force on charge. Perfect. So this formula that you see at the top here is the same one as we see it at the down here. So we've just made the force the subject as what? QE. And there's a negative there. I'll explain that. Now, drift velocity here relates the force, relates the electric field itself. Now let's hold on to the electric field. I want to show you something particularly with the drift velocity. Now, you know, when electrons are in a material, in fact, it has nowhere to go. If the material is something like this, it doesn't have the sense to move left, right, or go straight. It can actually be vibrating and just be colliding and will be moving in this kind of a form. Is that okay? Just moving anyhow. Now, we want to tell the electrons to exit from this area. So come this way. And because of that, we apply some particular electric field. And know that the electrons in these materials, there are millions of them. And We are interested in the distance that these electrons started when we applied the electric field and where it ended. Is that okay? And interestingly, someone may think, oh, when we apply the electric force, they all go straight and it goes to its destination. But interestingly, it doesn't work like that. Even after applying the electric field, there are a lot of things that goes on in there. So you see electron move from here, go 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 here, before it gets to the final destination. It actually behaves like a child that you sent. Oh, Jane Koto we was store never hire bra. Brazil, the child exit, sees a friend, see some people gossiping, go and stand beside them, see something on the floor, go and take it. You know, that kind of a movement till he or she goes and come back again. So it is very important to know how electrons actually behave in a material. And there's a formula for that. I think this thing, I've done it with you. I don't know. Did you do something like this in electrostatics? Or we don't remember? So if we are calculating the drift velocity, we have our drift velocity to be equals the mobility of the electron multiplying the what by the electric field itself. Now under drift velocity, we can have something we call the mean free path. This is also relatively very important. In fact, you know how when you are, I don't know where individually where we are, let's say those who are in Cape Coast or Kumasi, or let's say even Accra, Makola, if you are in Kumasi, KGT, if you are in Cape Coast, you are talking about Abra, okay, either Abra market or Kotokraba market, you know. So when you enter the place at a normal daytime, there are a lot of vendors around, people are moving up and down, but you can still get the space to move. So you can either move, then, you know, move around people and go. But let's imagine that same scenario, people are sitting there, then all of a sudden rain starts. Imagine how your movement is going to be. Going to be very hectic. Everyone is moving. There's a lot of chaos. Is that okay? People are hitting you up and down. People are pushing you because we are all trying to find shields. Now, the most important thing that I want you to know is if we are talking about something called the mean free path, we are talking about the distance that I am covering before I collided with another electron. Is that okay? So let's say I'm in Kotakara market. Before it started raining, I want to know the distance that I move before I chance on someone. I want to know the distance I move before I chance on someone. And you know, before I enter the market and exit from the other end, I have hit people and chance on people like 80 times before I exit. That small distance, that distance is what we call the mean free path. So let's say if I chance on people 80 times, I have 80 different free mean path values. Right? Then look at the distance that I am covering before I chance on people. Let's say for every distance that I cover, averagely we are talking about say 4 meters before I chance on someone. 4 meters is too long. Let's say 1.2 before I chance on someone. Now let's look at the situation where the rain has started all of a sudden. Do you think I'll still need a 1.2 before I chance on someone?
No.
Why?
Because at that time, everybody's moving busy. People will be crashing you. So you not get you not get that time to cover that distance before you go down. Everybody's now moving. There's chaos
Thank you. Thank you very much,
Yeah.
Lucky. But everyone is moving. It will be very hard for me to get that 1.2 meters. I may be getting very, very less. Like, let's say even 0.2, because you move one step, someone is there. You move one step, someone is there. You move one step, someone is there. So the distance becomes very, very short for the free moving path. Now, it is the same situation how electrons behave in a material, either in an insulator or in a conductor. In fact, if at low temperature, the mean free path is very okay, the distances are okay. But in a situation where there's a lot of chaos, and here the chaos is temperature, we increase the temperature, every electrons are vibrating and other things, and they are a little bit moving. So before you start your destination, to end up to where you are going, you would have chanced on a lot of electrons. In the process, reducing your what? Your mean free path. So you can see that the distance in the mean free path in a high temperature is way lower than the distance in the what? In the mean free path that in a lower temperature. In a lower temperature, you get high distances. In a higher temperature, very, very small distances. Have I managed to confuse you enough? I'm convincing you. Now, there's one thing of interest here. So let's keep what I've explained to you. I'll come back to it. The formula here is very important. So please keep it in mind. Now let's come back to our combinations here. Now, if we have a situation like our intrinsic semiconductor, and as I explained earlier, I've explained all these things. At high temperature, the semiconductor becomes a conductor. At low temperature, it becomes an insulator. And one way is the doping. In the doping, we have two types. We have the N type and we have the P type. The N type is interested as a donor. Is that okay? It's interested of adding an electron to the material, and that one will increase its conductivity. So when you look at the donor, all the electrons we have at the valence, instead of 4, so that it gets a good bond with the crystal lattice, it is 5. So the front 4 is going to bond, and the extra one become an SS to allow free movement. So now you look at something like phosphorus that we have, their valence electron, we have 5 of them. 1 here, 2 here, 3 here, 4 here, 5 here. The same way too. They are all at 5, 5, 5. Now, a typical semiconductor will have its bond something like this, and the phosphorus comes in, shares its 4 electrons, and an SS1 sits here. Now, with this SS1, this is how it's going to behave. One way or the other, one electron will eject and go to a different place. Right after injecting, we expect that a hole maybe is created, or let's say it's even ejected out and it sits here. But because there's an empty space, the SS1 goes to fill it, and another one may move, and because there's an SS2, this one will come and fill it. So at the end of the day, we have a lot of movement going on in the electron, and in the atom, or in our material. Let me say it that way. A lot of movement. And that movement is what we are interested in. So here we have a lot of our majority carriers as electrons and a minority as what? As holes. So in a typical semiconductor, that is N-type, when we applied EM field to it, so when we applied electric field to it, so this is our battery, this is our battery, And when we applied it to it, we expect the direction of flow of current to be this. Is that okay? So a flow of electrons to be this going anti-clockwise. Now, anytime the electrons are moving, we expect it to move at the opposite direction of the current. So the electrons are moving, but we have some holes as minority carriers. The hole too may move. But because electrons tend to occupy the whole spaces, they looks like they are going on the right. So we have the electrons moving like this, and the holes also, sorry, the current also moving at the opposite direction, and the holes also sitting there for the electrons filling and ejecting. How this is behaving is the opposite of how the p-type is behaving. Is that okay? So the p-type to, the way I'm talking plenty, please, are you listening?
Yes, we are listening.
Yes, please.
Yeah. Mm.
The same way we have the p-type also behaving. By this time around, the p-type is an acceptor impurity. A typical crystal lattice, we need only 4 of the valence electrons to bond with its neighbors before we can get a crystal lattice. But this one is 3. So the first one bonds, the second one bonds, the third one bonds. We need a 4th one to bond, but we don't get, so it creates a what? A hole there. And that is how an impurity like this is added to what? To an electron. Sorry, in a material like an semiconductor. So now, because we have a hole here, this one ejects, come and fill here. Another time you see, because it has ejected, there's a hole here. You see another person come and fill here. You see another person, you know, that kind of a thing. They all be filling each other's spaces. And the movement that we have here, we are mostly concerned with the holes. Is that okay? So for a typical p-type semiconductor, our minority carriers is of course the electrons, and the majority carriers is of course the what? The holes. Now we have holes here that they are moving, right? So all these things are holes, and they are moving towards the right. And we have the electrons moving towards the right opposite direction. There's one important thing between these two. I don't know if you've, in chemistry, you've seen a law like mass action law before.
No, please.
No, okay. Mass action law is talking about the balance of how the concentration of a compound is supposed to be. So most of the times we have something like A, small a, plus B, small b. Then we do this C, small c. Have you seen something like this in chemistry before? I think it's very common.
Yes, sir.
So mass action law relates this one. It actually relates this. And you know, what is talking about is if we have an intrinsic semiconductor or even an extrinsic semiconductor, the concentrations of the holes that we have there and the concentration of the electrons that we have here, they are all in equilibrium, like thermal equilibrium. Is that okay? So when you look at the formula like this that we have here, this is the concentration of the electrons. This is the concentration of the holes. We expect that for the intrinsic carrier concentration. When I say intrinsic carrier concentration, I'm talking about the concentration between the two of them, and all the concentrations that we have inside should be square of it. Is that okay? And in as much as doping changes things, it doesn't change the concentration of the electrons that we are having, or the concentration of the holes that we are having. Is that okay? So these mass action laws work for both an intrinsic and an extrinsic, but the formula changes a little, which I'm going to show you. So the formula that we have here is for a typical intrinsic semiconductor. Now let me show you for an intrinsic semiconductor how it behaves. Now, in normal material, where we have the material to be electrically neutral, we expect that if we have an electron and we have a donor, this is an acceptor, and we have a hole and we have a donor, they're supposed to be balanced. The number of concentration that we have here should be the same number of concentration that we have here. Now, in a typical N-type semiconductor, we expect that because, let me go here, because we have a typical N-type, for a typical N-type, we know that we have more electrons than holes. So at the end of the day, this one is negligible. Is that okay? And there's one thing that we have to know. For a typical N-type 2, I'm going forward a little. We expect that our acceptor here becomes 0. Now let's look at something here. If we have this one to be 0 and this one to be negligible, it means that at the end, we have N to be equal to what? ND. And if you remember our mass action law, NP is equal to what? The N squared for the intrinsic. Now we have redefined it in terms of N-type semiconductor. So we can replace the N here plus the ND, that's the donor. And our N come here, or comes here. And we divide it by our P. You can actually leave the formula like this, or some people will just leave it as P equals our N squared I on ND. And that is what we have here. And this is for a typical extrinsic semiconductor, like an N-type. Now, when we're talking about P-type, it changes a bit. Let me clean what I have here. So for the N-type, P-type, oh, let me clean. I'm writing with this thing, so I suffer a lot when I'm writing. Very good. So for a typical P-type, we have our holes to be very more than the electrons. So this one is negligible. Is that okay? Then at the end of the day, because we are talking about our host here, we don't need the donor in question here, so it becomes 0. So we have our, sorry, this is supposed to be, the P is supposed to be cancelled. I'm coming. Very good. So let me start from here. The actual distance start from ND, so that prevents a lot of writing. So a typical situation like this is how our electrically neutral material looks like. Now, if we have our P more than the N, ideally it means that our N becomes negligible. Is that okay? This N. And our N donor becomes what? 0. So at the end, we have P to be equal to what? NA. Is that okay? And this is our mass action law. So in place of the P, we just come and write what? NA here. And at the end of the day, we get our N to be equal to what? The concentration of the intrinsic divided by the what? By the acceptor. These two formulas are very important because at the end of the day, if you are given a question, it will be stated that you are working with, say, a P-type, N-type, or an intrinsic semiconductor. Is that okay? They are very, very important. So I have summarized these things in a chart here for you. That if I have N-type, this is the situation. If I have P-type, this is the situation. These are very important. Any question? I have another question for us to try. Should we move to the question?
Yes, please.
So take a screenshot of this one before I move to the next slide. This is the second question. Are we done? Have you taken a screenshot? Okay.
Yes, please.
Go back the first question. I didn't take down. Okay.
So unless you give us the formula, the formula for the N type and then the okay.
Please pose the question.
Please, are we done?
Yes.
Okay, so let's go through. So, who will help me? Maybe let's answer the question one after the other. Who wants to start?
One is D. Question one
No,
is D.
so you read, then you give us the answer.
Okay. Okay.
The type of atomic bonding most common in a semiconductor is the covalent bonding. It's a covalent.
Okay, the number 2 is helping us. Thank you, sir. Number 2.
The energy gap
Mm.
in a semiconductor: A, increases with temperature. B, does not change with temperature. C, decrease with temperature. And D is 0. The answer is decrease with temperature.
Okay, do you agree to that? Please, do you all agree to that? Okay.
Sir,
Yes, the
please.
last one.
Is answer again. I didn't get it.
He
Said the
says
answer is C, decrease with temperature.
Oh, okay.
yes. Please, the last question.
I wanted to know the explanation for that.
Okay, sir, can you help us with the explanation?
Yeah. As semiconductor gains heat, which is increase in temperature, it becomes more excited, making the electrons to move freely. And that kind of movement is as a result of temperature being increased. So as it's being able to move, it means that the gap is being decreased so that they can move from the valence gap to the conduction gap. Sorry.
Any different submission?
Sir, please. When temperature increases, the electrons get excited and collide with each other easily, so the mean free path decreases.
This one we are not talking about free mean path. This one we are talking about the energy gap. We are talking about the energy between the valence and the conduction.
Okay.
Yes,
Yes, it decreases with temperature.
as the temperature increases, the atom vibrate more. And so the more they vibrate, it also reduces the energy, the band energy gap. So it's the same.
Can we go to the last question?
An electron in the conduction band A has a higher energy than the electron in the valence band. B has lower energy than the electron in the valence band. C loses its charge easily. And D jumps to the top of the crystal. Has a higher energy than the electron in the valence band. That is A.
Are you okay with that?
Yes, I agree with you.
Okay, perfect. Now let's go to the calculation part.
The calculation part.
Who's going
I
to
had
help us?
1.5 times 10 raised to the power 10 cm cube. Negative cm cube.
This is per cm, not cm cube. Or you had cm cube rather.
Yeah. Sorry, per cm. Sorry. You know the
Okay.
formula is the n NCC square over the ND. That's the so the NCC square is giving the question as 1.5 times 10 to the power of 10. So you square that one divided by the N dupy. That's the N. The ND. The N dupy is same as the N. So 1.5 times 10 to the power 10 square divided by 1.5 times 10 to the power 10. You will still get 1.5 times 10 to the power 10. Yeah. That's what I had.
Okay, so tell me the formula. So you had you squared the NI, right? And you
Yes, I
divided
squared
it
the NI by the ND.
by the what?
The ND, that's the N dupy. That's the N. The N is same as the N dupy.
Okay. Any different answer so far? Yeah, hello.
No, please. I also got the same answer.
You got the same answer. Perfect. Any different answer? Okay, then it means we are good. Now let's go on to something important too. I showed you drift velocity. We have something also that we call the drift current. Is that okay? And drift current is just interested in the movement of these charges. And the last, I don't know if in electrostatics, we learned that anytime we are talking about current, we are talking about the movement of charges with respect to what? Time. Do you remember something like that?
Yes, please.
Very good. Is that okay? So it is very important. So drift velocity, drift current, as drift velocity is talking about the distance that it's actually covering with respect to time. The drift current is also talking about the movement of these charges with respect to time. But you know, in a situation like this, we need we actually need a field, electric field, before we can make this movement possible. Is that okay? So the movement of these charges are very important, and the direction in which they are moving is also important. Is that okay? So I made two important points here. Electrons move in the net direction opposite that of the what? Electric field. But in the holes is different. The direction in which the hole is moving is the same direction in which the electric field also moves. In fact, in the conductivity calculation, there's a long procedure before we get this. We don't need that. It's okay. You don't need to know that. But we can actually relate conductivity with respect to current density, with respect to the mobility, with respect to the concentrations that we have in the material, and even conductivity and resistivity itself. In summary, this is the whole formula. Is that okay? This is the current density, the J. And if you remember, the time that we are doing electrostatics, we mentioned current density. And the same as you know how density relates a mass and a volume, the same way this also relates. It relates the volume and the mass of the current that we are dealing with. Is that okay? Now, if we are looking at this in this perspective, it means that anytime we have, let's say, a current density, which is actually current divided by area, and we have the electric field, and we have the charge, we can also find the conductivity. Now, conductivity is actually related to this whole thing here. Conductivity is actually related to this whole thing here. So we can ignore this and write our conductivity here, multiply by the electric field. Is that okay? Now, when you look at the conductivity also is dependent on what we are calculating for. Is it an N-type or a P-type? You know that anytime we are dealing with an N-type, we are interested in electrons. So here, a situation like this, the whole goes off. If we are dealing with N-type, so here they will not, a question will not worry themselves, gives you the mobility of the what? Of the holes. It will rather give you the mobility of the electrons that you need and the concentration of the electrons. If it gives all of them to you, you are not using all of them. You are using the one that you are calculating for, provided it's an extrinsic semiconductor. Please, are we okay?
Is it provided? Is it extrinsic or intrinsic?
Extrinsic. These are all extrinsic. If you are given an extrinsic, you are not going to use the full conductivity formula. You need only one form of it. This is a full of them. You need only one form because one is more than the other. So if I'm given N-type, I'm going to use only this one so that my formula becomes the concentration of the electrons, the mobility of the electrons, and the what? And the charge. So, which is this one. In the situation I'm giving P-type, it means this one will cancel out and this one holds. So it becomes P, my mobility of the holes, multiplying the what? The charge. Now, if I'm able to find the conductivity, I can find either the electric field that I'm being asked of or the current density. Either of them works. Now, let's go through this. I've explained to you before how temperature actually influences the movement of either holes or electrons. Is that okay? They are very important. So the average carrier velocity, the average carrier velocity of a typical carrier is called the terminal velocity. So that amount that we need before it can move either an electron or a hole. Now, apart from this one, I explained to you how we can also use something we call the electric field. Another thing that also influences the movement is what? Is the concentration gradient, which we are going to talk about now. Now, the concentration gradient is very important because it has a whole lot of application. Now, if we have a particular material, there's no way that you see the holes or the electrons pushed to one side and there's a free space sitting there. And it's like how in SHS, in a dormitory, no, like even in the university, where students are going to learn in some of the lecture theater, and it's not lecture time, normal evening reading. When they enter, they don't sit beside their colleague. They sit at a distance so that they can concentrate. Then another person will come and sit. So when you enter a class, the class is full, but no one is sitting together. A lot of spaces in between, but they've all dispersed themselves. A typical lecture period, you see students sit at one particular end and the lecturer standing at one particular end to teach. It is not a uniform one. So you can see a typical diagram that I have here, where we have higher concentrations of electrons at one end and lower concentrations. This is a typical example of how a solar panel works. But because electrons don't have the ability to behave this way, they tend to move. So they will move. It's like diffusion, how diffusion works in liquids or droplets. You spray one end, at the end of the day, you can smell it at the other end. How osmosis also behave. Is that okay? But that one, you need a permeable membrane. Is that okay? So they have to move from one end to another end. And in fact, as I said earlier, that's how solar panel works. So the panel that we have here, it ejects a lot of electrons beneath the panel around this end. And now, because in diffusion and the behavior of the electrons, it's not possible for it to stay at one end and there's a lower concentration. No, they will move to a lower concentration. And when I say they will move, it doesn't mean they are all moving. They will move so that they spread out at the whole place. So because they are moving to this end, there's another plate here at the beneath here. That is our P layer, and that is where we get our power. Is that okay? So at the end of the day, the N layer is connected, the P layer is connected. We have a semiconductor material in between them. Is that okay? And the semiconductor material behaves in a situation where electrons don't have a concentration built at one end. They have to move. So when they move, the two layers gives us energy, like light. So now, when you look at a typical non-uniform motion like this is how we expect it to move. And the end result becomes. So this is how the diffusion happens in semiconductors. In fact, there's a property in calculating the diffusivity of the material. And here we are interested in how quick the electrons are able to occupy the free space. Is that okay? And the unit here is centimeter squared per seconds. And it makes sense because for a particular area, we are interested in the time that it will use to cover that end. Is that okay? So this is very important. So let's keep this one in mind. There are a lot of formulas pertaining diffusion. We don't need them actually, but I just managed to just bring about 2 or 3 formulas for just to show you, just in case one day you are doing a build-up in the electronics. At least you say, okay, I've seen this one before, but there's no way these things are going to come in your exams. Is that okay? So I just added it up. Or if you want it to come too, you can tell us, then we will find a way to let it come.
Yeah, sorry.
We beg you.
Oh, this is just a yes or no, say. Oh, let it come, say we will like it.
It can never be yes.
No, 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 no.
It shouldn't come. It shouldn't come.
No.
Okay, that is fine. But so now let's go through this. Now we know N type and we know P type. Anytime you are talking about N type, you are talking about excess electrons. Anytime you are talking about P type, you are talking about excess holes. Now, in today's semiconductor, we are able to merge the two of them together to form a very nice device. Now, this is what is going on. I have excess holes here. I have excess electrons here. And I merge the two of them together. In fact, after merging them, a very interesting thing happens. It's like we are in a class and the guys are sitting at one end, the females are sitting at one end. But because we've merged them together in one room, they are not feeling very comfortable. The women want to jump to the guys end, the guys want to also jump to the ladies end. So we give them that freedom. Mingle. So you see the electrons that we have here going here. The holes that we have here go in here. In fact, that pair manner happens to the extent that for some time, you get some people that are not able to mingle. We get some people too at the ladies' party that are not able to mingle. But at the end of the day, they are still at the electrons are still at the host side. The host two are still at the electrons side. So those who were not able to mingle try to see if they can mingle with each other. And that is where they end up here. So you see the electrons was here. It went here to mingle. It didn't work, and it ends up here. The holes are here. It goes here to mingle. It doesn't work, and it ends up here. And that part is what we call the depletion layer. So this is a very typical device that we call the PN junction. Now, this layer is very important because they are a buildup of a lot of things that we are using right now. And the field that is happening inside, in fact, there's an internal field inside because there's a movement of something. Is that okay? Movement of electrons, movement of holes. The field that is happening, the electric field that is happening in there, we call it the height of potential difference. So this is very important too. Now, there are a lot of things that we can do to overcome this depletion layer. The depletion layer can be widened where the excess has ended up. I'm talking at this end. They can be widened, they can be shortened. In fact, they can be shortened to the extent that you will not even see their presence there. They can be widened to the extent that it will not allow anything to go through it at all. Now, let's go on. Now, please, are we appreciating it a bit?
Yes, sir.
Yes, please.
Now, there are a lot of applications in these things. I mentioned earlier the diode, the LEDs, the LCDs we are using now and all. Is that okay? They are all built up in the property of this PN junction construction and operation. Now, I told you there's an internal electric field inside. We want to apply an external electric field to this situation. And anytime we applied an external electric field, we form something we call a forward bias or a reverse bias. Now I'm come to show you how the forward bias behave. When we finish, we go to the reverse bias, then we go to an ohmic material. Now with the forward bias, we've applied an external EM field, like a battery. But these are holes, and these are the junctions that we've created. Those who are not able to mingle. This is the problem they caused. But we have our holes, we have our electrons. But interestingly, because when we apply an electric field, the charge here as positive holds on to the charge here as the holes as positive too. And we know this from Benjamin Franklin. If they are positive, they will repel each other. So interestingly, this charge here tends to push the holes towards the depletion layer. The same way for the negative part. So we have negative, we have electrons here. Because of that, it tends to also push it to this end. Now, let's look at this. Let's not think plenty. If we are pushing these holes and electrons together, what do you think is going to happen to the layer?
They overlap and the layer will not be there. They'll overlap or they'll come into contact and the layer will appear.
So the layer will be closed or shut down with time.
Yeah.
Charges will tend to overflow, like to pass through now. It's like small children making a barrier that they will not let an old person pass. Just push away and let me go through. You know, very, very easy. But in a situation where, so these are just points that I've added. When you are reading, just take notes. Is that okay? So there's a narrow in the depletion layer, then the barrier potential reduces and other things. It's just for students reading purpose. So I'm just explaining these things. Now, in a situation with the reverse, it's quite different, you know, very, very different. Instead of, just a minute. Yeah, hello. Please, can you hear me?
Yes, sir.
Perfect. So this time around, the situation is going to change from what we saw earlier. You see, before we were having our electric field, the charges, the positive was here, the negative was here. This time around, it's changed. So if it's changed, you get the holes here, that is our positive charge, tend to move towards the negative. And the electrons here, that is the negative charge, tend to move at the what? At the positive. From Benjamin Franklin, positive and negative are attracting. The negative and the positive are also attracting. So this time around, because we are all pulling them away from the depletion layer, it tends to behave different here. So we tend to get a wider layer this time around. And as we increase the layer, it becomes very difficult for current to pass through this kind of a diode. Is that okay? So it's like my high school. Anytime we are having a dining, we tend to break the door because everyone wants to go, and we say capture the ladder. So if you capture the ladder, it means you are going to serve on that table. And if I'm able to serve on that table, it means, of course, I'm getting more food. So something like that, you can put a scenario like that, pertaining the forward biased PN junction situation. We were strong enough to break some of the dining, sometimes break the dining gate. But the school also was growing wiser. The more we break it, the more they were finding solutions to the problem. So a time came, it will be very difficult for you to even break because of how they designed the doors. Is that okay? And you can think about that one as a reverse bias. So now the depletion layer has increased, like very increased. And it has, in fact, the more we applied electric field, the more we are increasing it. We can increase it to the extent that a time will come, the junction or the diode even breaks. Is that okay? Because we are still increasing the layer. Current 2 is trying to also move. Are we getting this thing a bit? Perfect. Now, let's hold on to the forward and the reverse bias. I'll show you something briefly. But before that, let's look at a material like an ohmic material. I think level 100, you did one experiment where you were applying current and measuring voltage. Did you do something like that? Perfect. If not even your recent switch program, maybe I think those who are in UCC here, they will definitely do it because it's here, the setup is here. So in a simple schematic diagram like how we have it below here, I can be applying current to, let's say, R, my material R. Is that okay? Then I'll be measuring its corresponding voltage. So maybe from the current, I'll start applying 2 amps. Then I'll go to 4. Then I'll go to 6. Then I'll be measuring the corresponding voltage that I'll be getting that is passing through my material, whether copper or aluminum, which we mostly use in the lab here. And when I finish, I will do a plot between the two of them. The plot between the current and the voltage can help me deduce the resistance, because slope is between the voltage and the what and the current. A typical situation like this, if I do the plot and I get a straight line like this is an ohmic material. That is how I'm expecting the graph to be. But interestingly, semiconductor doesn't behave like that. You can get current being alternated with respect to voltage and measuring the two of them at the same time. But it will be very difficult, and it's not even possible for you to get a straight line for a typical semiconductor. Do we have any idea how the graph is going to be, or the line of graph is going to be for a typical semiconductor? Any idea? Any idea?
Say,
Yes, sir.
I think we'll have a curve graph.
We have a curved graph towards which side, moving to which side?
From current to voltage.
Okay. When you say curved, how curved is it going to be?
The curve. Instead of us getting the straight line, we wouldn't get it like that. So you see that some of the proteins, it will just give a curve. If I have a whiteboard, I could have, sketched it for you to see.
I'll be so proud if you do that for me to see. So how do you do it? Maybe you can sketch it on the paper, then you do a video. You turn your camera, then you show it to us. As we are waiting for Saint France, any different submission? What is going to happen if the material is a semiconductor? This is for a conductor. We want to know how the semiconductor will behave. Are we thinking about it?
Yes, sir.
So, fine, did you say yes or no?
Yeah, thinking about it.
Yeah, Sir Frank, hurry up. Sir Frank, I'm waiting for you. Hurry up. Any answer for me so far? But do you think a semiconductor will behave the same as how a conductor behaved? Maybe let me ask this first.
It
No,
will not.
sir.
It will not.
It will
It
not.
will not. Okay, that's a nice step. So now the problem is how it will behave. You know that it will not, but the problem is how it will behave, right? Okay,
I
then let me
think
try.
it will curve up towards the voltage.
It will curve up towards the voltage. Okay.
Yes, from the origin.
Do you know how a
I
quadratic?
say,
Yes, I'm listening.
I agree. I agree with you.
You agree with me?
It's- Yeah, instead of moving straight, it will be turning towards the voltage.
I've not said
It will
any
move closer
answer.
to the voltage side.
So, like,
Now, what
what are you agreeing with? I didn't see any answer.
no, what Sir Mohammed said, the line,
Right.
it will not be straight. It will rather move it towards the voltage side. I'm talking on the
Oh,
ground.
okay, that's perfect. Then let's go. So, before I show you how the curve actually behaves, do we have any idea what a diode is? Have we seen a diode before?
Yes, sir.
Yes, sir.
Where did you see it? Did you use it to teach for something?
Yes, sir.
Okay. How did you guys use it? And how is it like? What is it used for?
When you connect it in one way, it allows current to flow, and then in the other way, it prevents current to flow.
Oh, interesting. Okay. But the level and the students you teach, do they need to know that?
Says in their curriculum.
Learning about diodes.
Yes, sir.
Yes.
Okay. Na ọmụ si asa na wee ni na ọmụba SHS na high school university a ehu dị ọmụ si ano because I'm teaching electronics level 200. Ubusa ọmụ hwẹ ọmụ ni mu. Anyways, it's fine. Let's look at
They
how
even do transistors.
they do transistors too. Interesting. I promise you, bida. So some of them they've not seen it before. So you have to like show it to them, or maybe they know and they've forgotten. I don't know, but I really know they do all these things. Anyways, let's look at how for a particular diode we've connected an electric field to it. Now you know how a forward and a reverse behave. For a typical diode, I'm going back. For a typical diode, this is where the cathode is, and this is where the anode is. So this place that I have the leg, like the long, and this is the schematic anyways. So anytime you see a schematic diagram drawn and you see this, it means it's a diode. And this is where we have our cathode, this is where we have our anode. Now I want us to look at this in a schematic form. If we applied an electric field, how is going to be a forward and how is it going to be a reverse? So when you have something like these two diagrams, so one here, and I think this is the second one. Which one is a forward and which one is a reverse?
The first one is reverse, and the second one is forward.
The first one is what? Let's look at it very well, I beg.
So the one on the left is forward, and then the one on the right is reverse.
So this is one, this is two. Frank, are you convinced or you are still confused?
So one is
Maybe
forward and two is reverse.
Very good. So one is forward, two is reverse. This is here my cathode. This is here. Is that okay? And please excuse me, let me pick this call. Okay, so sorry. This is the cathode, this is the anode. The same way this is the cathode, this is the anode. Do we all agree the first one is the forward bias? Do you agree to that?
Yes, sir.
Do you agree the second one is a reverse? Do you agree to the second one is a reverse?
Yes,
Yes,
please.
please.
Yes, sir.
So now let's go on to the curve I mentioned earlier. How a forward behave and how a reverse actually behave. Now let's look at something that we have here. I'm zooming in. So for a typical current and voltage, forget about, when we have something like this, we have 4 quadrants. So quadrants 1 up to the 4th one, right? Forget about all the other quadrants. Let's think about only this part. Is that okay? The top right. Can we all see that? So when you look at it, we've plotted I and we've plotted V against each other. This is our voltage, this is our current. The current is in milliamps, right? Ideally, for a typical ohmic material, we expect to start from here and go straight line to the top. The small changes we get in the voltage should be the same small changes we get in the current. But interestingly, it doesn't behave the same way for what? A semiconductor. The semiconductor is very dependent on the type of electric field you are applying to it. That will influence whether current is going to go through or current is not going to go through. And the polarity you're giving to the what? Semiconductor. Whether the positive is connected to the N type, the negative is connected to the P type, that kind of a thing, So it's very, very dependent on it. Like very, very dependent on it. So when we take a typical one like what we have here, the voltage that we have, the V. When you look at this, but before that, hold on. Can someone explain this graph to me, please? Any idea? Can someone explain what is going on? Are we thinking about it or Asamaba?
Thinking.
Okay, so I'm giving you only 2 minutes. If anyone is done, the person can start talking. Let me see how you understand this. And anyways, you know how a forward bias arrangement is done. I just shown it to you. And the V here is the electric field. We are getting this one from the electric field. And the current here is the currents going through all the circuits. Is that okay? So please try and give me an answer here. Let me see.
So I think that when you start applying the voltage, we need to apply enough voltage in order to break the barrier potential. That's why the graph is what moving like somehow horizontally towards the voltage side. And after breaking the barrier potential, the current what will increase suddenly because of what the exchange of charges across what the junction.
Okay. Sir Philip Sarkodie, I'll give you.
Yeah.
Do you want me to score you?
Okay.
I'll give you 6/10. It's good, but I still want
The
more.
the nil point. The nil point is where the curve starts to bend up.
Okay.
You
So
know,
what does it imply?
before the nil, yeah, before the need to, it's cutting. The green line cutting first.
Mm-hmm.
And so when it's cutting, then when it gets to the nil side, that's where it started bending upward.
Okay.
So I want to come in.
Yes, coming.
So I can see that at the initial stage when the voltage was small, it looks like the current was also very small. It looks like the current is not even flowing. But when the voltage passes the knee or reaches the knee, then the current begins to rise quickly.
Is there any different submission apart from self-function? Any different submission? So should I come in? Okay.
Yes, sir.
So what everyone is saying is correct, but I need a full explanation here. When the forward bias, we have a layer in between the P and the N. And as I told you earlier, when we applied EM field, electric field, sorry, we are pushing the charges in the P type and N type together to close the layer. Is that okay? So from that time that we started applying the voltage, current is still not going through. Current is still zero. And that is the point where we have the straight line. So current is still zero, but voltage is increasing. Voltage is increasing. Voltage is increasing. Now, when we reach this knee part, that is where the layer has broken. And as I told you about my SHS story, we are all behind the doors. A buse came. You deny the speed being in the room. Is that okay? So the first thing is breaking the path and the speed that, because everyone is behind you. What tough from corner here bit also? You understand? That is how hunger was reaching at that level. Because everyone wants to go and catch the ladder. So right after breaking the door, Vim bin in Naideko. Vim Naideko, that is what increases that sharp movement here. And that part, you see, we don't need to apply huge voltage, very small voltage, but look at how current increases up. There are a lot of powered up current there. It's in a breaky and current is increasing. And that point where the layer breaks is the knee. Are we appreciating it a bit? This is very important. Now, the explanation that I have done here, do that in Keche here for me, for the reverse. Hold on. Let's all think through, take our time and think through this. Just read the things that I'm showing you here for like a minute or two. Then we answer it. Is that okay? Please, are we done?
Hello, sir.
Are we done?
Yeah, I want to say something small.
Yes, can you say something small?
So I think for the rivers, at the initial stage, the depletion zone was very small. So we could say there could be some small chance of a current passing. But as the voltage is supplied, the depletion zone begins to widen up, decreasing the chance of a current passing. So that's why we see in the diagram the current further reducing.
That is perfect. But we didn't talk about the reverse breakdown of voltage. So use the graph. You see there's a part that it breaks.
Can I come in?
Yes, please. Say come in, Saturday.
Say, it means that at a particular voltage, the junction, the barrier will break down. But it seems that after the junction is broken down, the voltage will remain what? Will remain constant.
Okay. That's a nice admission.
So it means that when we reverse bias a system, after breaking the barrier potential, the voltage that you get to be a constant voltage.
This is perfect. You know, with the reverse, after, as Frank said, when it starts, the layer starts increasing. It increases to the sense that it breaks down. That section that it breaks down, that is what we call the reverse breakdown voltage. In fact, when it breaks down, it automatically spoils. It's okay. It's automatically spoils. It breaks down. It doesn't break down for current to go through or other voltages to still work. It breaks down completely and nothing works again. And that is why we have our line straight like this. So when it breaks down, that is all. And you can see that even our current here is in microamps, very small current, kind of go through, and that is all. There's no variation in increment in voltage that is needed again because it is broken down. So you can see that if the line could have even moved here, you could see that, okay, after breaking down, there's still some amount of voltage going through. But when it breaks down, no voltage goes through. We get a little, even current itself don't have to go through, but we get a little current that is actually going through. Are we following or we are confused?
We are following.
Perfect. And that is how a diode behaves. But because we have a forward and a reverse, they all have their own ways of this behavior in terms of forward and in terms of what? Reverse. So I've explained all these things to you. You can just take your time and read because I've added some notes besides them. Is that okay? Now, with the breakdown in the reverse, we have two. We have Zener breakdown and we have avalanche breakdown. And it depends on some conditions before we can get these two breaks down. And they all break down at different voltages. Is that okay? I think all these things you can just read them, but I've summarized them here. One breakdown is very, very dependent on electric field. Another breakdown is because of collision. That is for the Zener and the avalanche. And when you look at the Zener breaks down very early. The avalanche, it takes time before it breaks down. And their mechanisms are different, as I said earlier. One is because of electric field. One is because of what? The collision between the minority and the majority movement. Is that okay? This is very also important. So these are all some of the applications that we get with a diode. And a diode is a typical example of a PN junction. Is that okay? So PN junction is a diode. Even the LEDs too. A typical application are them. So I have a question for the class. We do this one, then we end the lecture.
Sir, please, before your question.
Mm.
I know we have a type of diode we call the Zener diode.
Mm.
So from what we see from the diagram, is it that the Zener diode works well in the reverse breakdown, or?
This is a nice question. I will show you a Zener diode. We will use it again. When I say diode here, it's a general form that I'm talking about. But in some application like building a power supply and other things, we particularly need a Zener diode. Is that okay? And even during amplification section too, we use some types of diodes. So we have a lot of different types of these diodes. So, and they all have their own properties depending on the application that you are using it for. Is that okay? So one may choose this because of this, one may choose this because of this. But I'll talk about it. Maybe not today, but I think maybe our next meeting I'll talk about it. Is that okay?
Okay, sir.
Any different question? Okay, so now let's do this. How many minutes do you need to do this? Will 5 be okay? Okay. Hello, we are keeping on all.
We are done.
Really? I'm still sitting here waiting for. Oh, okay. So what is the answer? Can someone take me through? Sir France.
The A1. So
No,
the
so
question.
you read. Hold on. So you read the. Help me read the whole question. Then
Okay,
you
said
answer only the A. Mhm.
right. The forward characteristics of a diode is shown in figure. Use the characteristics to determine A, the current flowing in the diode when a forward voltage of 0.4 volt is applied. So I just go to the graph and 0.4 volt. I trace it to touch the curve there and the corresponding current there. I'm getting like 1.8
1.8 what?
milliamp.
Milliamps. Perfect. Thank you very much. Can someone help me with the B? Hello, can someone help me with the B?
Yes, sir. So the voltage drop across the diode when the voltage current of 9 milliamp is flowing it. So I got almost 0.7 volts. That is about 0.68 volts.
Okay, 0.68 is fine. But when you take 0.7, it will be wrong.
Yes.
So 0.66, 0.67, 0.68 is fine. The question, the C.
Okay, so the C. The resistance
Please,
you have to
please,
calculate.
just a quick question. The B, no. Also, if you do
Mm.
0.5, 0.5, I don't know whether it will be correct.
Oh, it exceeds 0.5. 0.5 is around this end. So the range that may be marked correct will be around 0.6. 0.5 required. 0.5 is around this end.
0.68, 0.69.
Yeah, 69.
0.67.
It means 0.66 to 0.68. Is that
Yeah.
okay? Here it's not calibrated, but at least we should be able to use our eyes to give a good value. Is that okay? Yes.
Okay.
Please
So
go on.
the C, the C type, the C. And so you have to calculate the resistance of the diode. So from Ohm's law, V is equal to IR. So the resistance, which is V, R is equal to V on I. So the V is 0.6. So when you trace it to the current, you also get 6 milliamp. So we have 0.6 over 6 times 10 to the power minus 3, which will give us 100 ohms.
100 ohms. Are you sure about this answer?
Hello, I can also come in.
Okay.
Should I?
Yes, please.
He said he had 100 ohms. Okay. I also saw it like, as he said it, the Ohm's law, the resistance is equal to voltage on current. So we have the voltage as 0.6 on 6. You should give me 0.1.
Okay. And what did you do with the millivolt?
The milli one. So I multiply
Millivolt.
by times 10 to the power minus 3. And I'll get what?
No, then that you should multiply by 10 to the power 3 rather. Because the 10 to the power minus 3 is added down.
So the answer is 100 ohms. Are we all getting 100?
Yes, sir.
Now the
Yes,
last one.
100 ohms.
Mm-hmm. Yes, the last one. Nasema now.
The last one is an SI silicon type.
Why?
This one being boot.
So it's,
Okay.
it's a silicon diode.
It's a silicon.
Oh.
So now let's look at something here. Anytime we have silicon for a forward bias, silicon breaks down, so germanium breaks down earlier than silicon. I can move up to 0.5 and silicon is still working. It breaks down when I'm at 0.7. Germanium breaks down at 0.3. I was thinking you've seen this, that's why I didn't talk about it. So they all have their different knee points. Is that okay? The point where it allows current to go through. Now in the question, we are asked to find whether the type of diode is a silicon or a germanium. Which one is it?
Silicon.
Why is it silicon?
It's silicon because the voltage for the breakdown
It's between 0.6 to 0.7.
0.4.
It's what?
No, the breakdown. The breakdown, 0.6 to 0.7.
No, it's not a range. Oh. Let me show you again. Germanium breaks down. Not even, it doesn't even break down. It allows current to go through. That is the knee point or knee voltage at 0.3. That is germanium. It's not a range. If the material, because I told you we have two different types of material in semiconductors. Like we have a lot of them, but the two types that we were looking at it was the silicon and the germanium. Is that okay? And we intentionally focus on only silicon. And the knee voltage is the point where it allows current to pass through the diode. And now they are saying that anytime the diode is made of silicon, the knee voltage is 0.7. Anytime the diode is made of germanium, the knee point is 0.3. Now, from the diagram here, what is the knee point here?
0.4.
0.4.
Say 0.6 to 0.7.
0.6 to 0.7. Okay. The knee point is actually around this end.
0.1.
Yes, around this end. 0.1 will be too low, but around 0.2 to 0.3.
There's 0.3.
This is where the knee
Because,
point is.
where your cursor is.
Yes, it's around that end.
And
So
that
when
should
you
be
look at
0.3
this,
something.
which
But,
material, because
but
I
sir,
told you that, yeah, I'm listening.
I can see a rise from the 0.1.
Yes, that is true. We want a point where we have a rapid movement of current. Is that okay? So all this part, current is not going through. But right after reaching here, it goes up. But when you choose 0.4, current is already at 2. After maybe, when you choose 0.6, current is already at 6. After maybe that. Is that okay? So if this is an exponential curve, we want that bottom curve there. Is that okay? Like a tangential curve, a line that we can actually draw around this end. So it's around this end. So particularly around this end, which material corresponds to around this end?
Is germanium.
That's germanium.
Is that okay? Because the breakdown, the knee voltage is 0.3. The knee voltage is 0.7. 0.7 is around this end. This is too much. Please, are you appreciating it a bit?
Yes, please.
Yes, please.
Perfect. The next time we meet, we will talk about load line, but I'll prefer to hold on with the load line, go and show you something about this circuit we have to do in terms of how diode characteristics that one I've shown you, how diode operation actually works. Then I'll come back to it. If there's a need, I will also just do it, because I was thinking of maybe going to do the AC part in power supply and coming back to it. But so far, for this particular part, we are left with only this force light, which I'll hold on to it for now, if there's a need. If there's no need to, I'll try and explain it before I go on to the next section. Any questions so far, please? Before I end the class.
Yes,
The
the
slide.
slide going to be
The slide.
available.
The slide. So, who is our course rep right now?
Sir, it's me.
Okay.
Frank.
So Frank, just
Yes.
say hello to me. Then I'll send it to you by I beg. Right now, there's a lot of
So
pressure.
you around what time?
Oh, no, you can say hello to me. By the evening, I'll send. If by evening you don't have it, you remind me. Right now, they will not send it because I have to do some small changes. Is that okay? And I'm going to teach too. So when I finish, I will send. So have a nice evening, everyone. I will try. I have missed a previous section. I'll try and cover up that one. I've not been feeling well and other things, so pardon me for that. So I'll try. So have a nice evening, everyone, and afternoon too.
Same.
Thank you, sir.